My name is Jie, and I'm from Netease Fuxi AI Lab, and my speaking partner is Zhao, who is from the NVIDIA. And the title of my presentation is Achieving AI Teammates in NARAKA BLADEPOINT Mobile PC version. And the agenda of the presentation has 3 parts. The first part is building the real-time voice-controlled AI teammates in games. And the second part is the GPU on device inferencing. And the final part is the NVIDIA in-game inferencing SDK. So let's start presentation. And before my presentation, let me give a brief introduction to the Fuxi AI Lab from Netease. Fuxi AI Lab was founded in 2017, and it is the first game AI research institute in China. Perhaps it is also maybe the first game AI research institute in the world. I don't know. And our Fuxi Lab has a very broad research interests, and including the computer graphics, computer vision, reinforcement learning, natural language processing, and speech technology, and some other AI technologies. And up to now, we have published more than 300 papers, and most of which have been published on the top AI conferences and journals, such as the SIGGRAPH, TPAMI, RCCV, CVPR, NeurIPS, RCM, RClear, and so on. And in addition, we have got more than 600 patents and have given more than 10 talks in the GDC. And in addition to conducting the technical research, our team is actively applying AI technologies in various scenarios. And until now, we have launched more than 100 applications covering a variety of scenarios, such as the gaming, entertainment, education, and more. And on July 25 last year, we officially launched the game Copilot, which is also called the AI teammate in the games NARAKA BLADEPOINT Mobile. And it is the first real-time voice AI teammate gameplay to be implemented in the world. So what is the game Copilot, or what is the AI teammate? I will use a short video to show what the AI teammate is and what functions and the features the AI teammate has. And sorry that currently the AI teammate in NARAKA Mobile can only support the voice interaction in Chinese. So the voice interaction examples showed in this video are all in Chinese. So please read the English subtitles and to understand the content of this video. So let's start watching the video.
在永劫无间中，网易雷火与伏羲工作室加入了大语言模型与 NVIDIA ACE 技术驱动的 AI 队友，让 AI 模型运行于客户端。
我们这把想跳去哪儿？
听老板你的，你是高手。
那我们跳天人城吧。
好呀，这把我全力辅助你。
我去前面开个堆，能帮我去前面敲个钟，看看有没有人吗？
好的，我这就去，保证完成任务。
你的大招进度到多少了
？80%，马上就有了。
感觉有点危险，要不你来把我的金甲换上吧？
我真的可以拥有吗？谢谢老板。
能给我捡一把斩马刀吗？
这个我有，我来给你。
能再给我一个斩马刀的魂玉吗？
这个我也没有，我帮你找找。这里好像有敌人，老板小心！
你先撑住，我再搜一会儿再来找你。
我尽量拖住他们。
我快没血了。
这就开打，掩护你撤退。老板，有危险，你快去打药，我来拖住他们。
我马上打完药就回来。
老板别怕，我来扶你。
谢谢你。
Okay, I believe that through that short video, you guys have already gained a preliminary understanding of the AI teammates. So why did we come up with the idea of creating such AI teammates feature in the NARAKA mobile? As we know that for players who like playing the multiplayer competitive games, some of them it is hard for them to find suitable and reliable human teammates to play with them. And on the otherwise, for players who like single player games, such as those 3A role-playing games, it is hard for our game developers to develop a well-designed and a well-played AI companion system to enhance these single players' gaming experience. And we are, just as I mentioned, that we are a game AI research institute, and when our game development partners shared these confusions with us, an idea emerged in our minds. And can we take advantage of the rapidly advancing AI technology to create AI teammates instead of the unreliable human teammates to enhance the player's gaming experience? We had this idea, but how could we bring it to life? After our internal discussions, we believe that the reliable AI teammates should possess two fundamental abilities. The first ability is to play games, and the second ability is to interact with the human players. So as we know that we can enable AI to have the ability to play games through some traditional technologies such as data machines, behavior trees. But if we want or expect AI to have the ability to play the complex games well, we should rely on some cutting-edge AI technologies such as the reinforcement learning. So this page I will showcase the development history of reinforcement learning of the past decade. In 2013, DeepMind published a landmark paper in Nature. In that article, they used DQN, a reinforcement learning algorithm, to enable AI to play Atari games well through self-learning. And in 2016, AlphaGo stunned the world by defeating the top human grandmaster professional Go player, Licedo. And in the following years, the OpenAI and DeepMind also respectively using the reinforcement learning algorithm to enable AI to defeat the top professional players in two extremely complex games, that is Dota 2 and StarCraft 2. So these events demonstrate that we can use a reinforcement learning algorithm to enable AI to learn to play almost any games well. So it is a very good and powerful technology. On the other hand, obviously, if we want the AI teammates can interact with the human players, we should need to utilize these AI technologies such as the automatic speech recognition, natural languages processing, and text-to-speech technologies. And I think the most important and the key technology of these AI technologies is the large language models. So this page shows the development history of the large language models. The large language model have also been developing rapidly in recent years and have received widespread public attentions recently. And in 2017, the Transformers architecture was proposed by Google, and since then, the OpenAI adopted the decode-only architecture to develop the large language model technologies and released a series of GPT models. Until 2022, the ChatGPT moment arrived, as we know that, which triggered a new round of rapid development of AI technologies in recent years. And for me, there is another important moment, that is the moment of the open sourcing of Llama by Meta. Because since then, our community, including us, can apply this AI technology to develop customized AI applications based on these open sourcing and high performance models for our own AI applications. So with the support of these fundamental AI technologies, the new questions are raised. The first one is that, can we really take advantage of these AI technologies to create reliable AI teammates? And can we make the interaction experience of AI teammates identical to the real human companions? And for example, we want to have the AI teammates can have the low latency interactions features and the realistic voice. And the final question is that, can we make the inference cost of AI teammates low enough to both our game developers and our game players to afford? And that is very important because, as we know, that the large language model service is a little expensive and now. So before formally introducing our solutions, I will give a brief introduction to the game NARAKA Mobile. NARAKA Mobile is an action game with the Battle Royale game mode. And the map in the games is abundant in buildings and the diverse in sea mechanisms. And it is a high freedom system. Players can run, can jump, can climb, and it has a very freedom system that we call the free gambling hook system. That use this hook system, the players can reach every visible place. And also it has 3 mutually restraining skills: the normal attack, the charged attack, and the shock. And also it has a rich weapon system, and different weapons in these games have different features. And also it has a lot of heroes in the game, and each hero has its specific hero skill system. So these features decreases the difficulty for us to develop a high-level AI teammate to play the games. So based on these features I just mentioned of the game, and our goal that we want AI teammates can play the game well and interact with human players, we believe that the AI teammate should have the following capabilities. And the first capability is to play games. That means that the AI teammate should perform well in the game of skills, and cooperate well with the human players. And the second ability is that the AI teammate can accurately understand the voice commands from the human players and perform outstandingly, whether in searching and delivering equipment or in coordinating in team battles. And the third capability is that the AI teammate can observe the battlefield state and report the key information, and also answer the players' questions about the game. And the final capability is that the AI teammate should support the free voice interaction and provide players with a high emotional value. And so that means that it is not only a combat assistant, but also it is a reliable game partner. So in order to enable the AI to possess these capabilities, we have construct an agent system as shown in this figure. Okay, in this agent system, we have introduced many AI model services, such as the automatic speech recognition, natural language understanding, reinforcement learning models, large language models, and text-to-speech services. By rationally organizing these atomic AI services, we have initially built an AI teammate that is initially usable for game players. But however, we have found that there are still many challenges for us to in getting the game developers to accept the AI teammate feature, also to truly enhancing the players' gaming experience. The first challenge is to improve the open mic speech recognition performance. Under the real-time interaction with an open mic without an wake-up word, there are various non-player vocal inputs such as the noise and the multiple speakers and ambient sounds will be put into the ASR model. And also there are various terminal phones with different hardwares, and there are different accents, dialects, as well as very professional terms, specific abbreviations, and these conditions both increase the difficulty for the ASR model to accurately understand the player's speech. And the second challenge is that the AI teammate should understand the player's commands and act reasonably. That means the agent system should identify the player's commands in the free chat and respond accordingly. And if there's no instruction, how can the AI make the reasonable behavior decision? And how to maintain the AI's strength while following the player's commands, maybe not suitable commands. For example, that if the AI teammate nearly to kill an enemy in the battle, but the player give a command that let the AI teammate to come back and support him or heal him. So what the AI teammate at that time should do, if he should he to continue to kill the enemies, or should he to come back to support the players? So it is a hard decision for the AI teammate. And the third challenge is that we should to reduce the system's latency and the cost. That means that how to achieve low latency voice interaction similar to GPT-4o, providing a seamless player experience comparable to human interaction with AI, and how to minimize the service cost while we have involving so many of AI capabilities. So the solution to the first challenge is the closed loop data system. The left picture showed the closed loop data system. The daily test and the online data will be sent to this system, and the active learning module in this system will filter out the valuable data, which will be automatically sent to the crowdsourcing platform and annotated by our crowd. And then the model training process will use this annotated data to train a new model. If the new model passes the model evaluation, it will be deployed online, and the online model will be updated. And then the new loop runs again. So the right picture shows that after the implementation of the closed loop data system, the performance of the ASR model has been significantly improved, especially for the indicator of the noise detection accuracy. As we can see in this in right picture that before the closed loop data system, the ASR model really has the ability to detect the noise. And after the closed loop system, the improvement of the noise detection accuracy is extremely remarkable. And in this page, we can observe the same performance improvement in the natural language understanding model. And after going through the closed loop data system, the overall capabilities of the natural language understanding has been significantly improved. Okay, the solution to the second challenge is we use the reinforcement learning. As we know that I mentioned that we can reach every visible place in these games. So it is very hard for the AI teammates to navigate in the games and combat well with the human players. So we adopted a learning strategy combining the reinforcement learning and self-imitation learning to improve the general navigation capability. And the program will automatically collect the high failure rate scenarios during the training process and automatically design the targeted courses for reinforcement learning. And for some particularly difficult areas, such as in the caves and in the door rooms, we introduce the passkey point method to improve the ability for these very difficult corner cases. That means that in some caves, the exit path of the caves will be passed by some special places. So it is very hard for reinforcement learning to find these special places where he wants to navigate to the exit. So we introduce some midpoint in the training process to simplify the training process. We also use reinforcement learning to combine the combat reward and the command following reward, so the AI can follow players' commands without reducing the combat capability. And for some non-combat commands, such as the searching and delivering for equipment and exchanging items with human players, we just use the behavior tree to achieve these behaviors. And the left chart and the right table showed the improvements after this optimization work. For navigation capability, the AI got a 99% success rate after various optimization methods and reached the level of skilled players. And for the combat capability, through the reinforcement learning with commands, the AI can still observe the battlefield environment, follow the command, and make the appropriate decision, and still maintain a high combat level, which surpasses the 19% players in these games. And the solution to the third challenge is just the engineering optimization. As we know, there are many AI model services in this agent system, and through the entire system, we have entirely adopted gRPC as our communication method between different services instead of the RESTful API and the like. And additionally, for the large models, of course, we applying the quantization method to enhance the inference efficiency. And also, we have introduced the trend inference server as our inference engine, and with its dynamic batch inferencing the feature and the throughput of this system, including each AI services, has been significantly increased. And for large language model, we use the VRM as our inference framework, and also we transfer the raw PyTorch model into the TensorRT version to improve the inference speed. Also, we have do a lot of work to simplify the system's service architecture, and we do as much as we can to simplify this service system. And the figure on the right shows demonstrates that after various optimization work, the inference time of each service has been significantly reduced, and the response time of the entire system, just the agent, can be controlled within 1 second, which achieving a near real-time voice interaction with human players. Especially, you can see in the picture that the text embedding service and the ASR service and the text-to-speech service. After this optimization, the improvement is very, very significant. Okay, and this page shows that after this optimization work, not only had the response time of the entire system has been reduced, but also the inference cost, which is very important for game developers and the game players, has also been significantly decreased. We can see that for large language model, the majority of the cost of this system is the large language model service. Using this optimization work, the cost of the inference has been significantly reduced, and also the same phenomena can be seen in this picture, that the text-to-speech service has been reduced. Besides the optimization work on the cloud version, on the NARAKA mobile PC version, we migrated some cloud services to the PC edge clouds to the PC edge side and conducted the performance service just as shown in the left picture. And we found that with the large language model service, the RTX 4090 chip on the PC offers a faster inference speed than the L20 chip on the cloud. And the overall inference latency and cost will be further reduced on the device version. And on March 27 this month, we will add a locally hosted NVIDIA ACE powered AI teammate to the NARAKA mobile PC version. That, yes, it will be released soon. And for the future work, we still aim to enhance the player's gaming experience. We plan to boost the large language model capabilities. Maybe we will use the better open sourcing model to fine-tuning the model, and we also want to collect more players' data, the dialogue data, to improve the model's capabilities for large language models. And we also want to improve the voice interaction experience. And further, we still want to cut down the service cost for the entire system, because, as I mentioned, the game developers are very, very clear about the service cost. And what's more, we are we intend to explore more AI gameplays in the future. And one of the explorations we are doing is the AI coach. And the AI coach is distinct from the AI teammate. The AI coach will not play the games directly. Besides, it will observe the player's playing process, and he maybe detect that what knowledge the players familiar with, and what knowledge that the player is not familiar with the game. So the AI coach will give the personalized guidance for the new players, and we think that it is very important for the new players to familiar with the new games. And okay, and that is all my content. And let's welcome the Bill Zhao to continue the presentation.
Okay, thanks, Tangjie. Hello, everyone. My name is Bo Zhao, Developer Technology Engineer of NVIDIA. For GPU on-device inferencing, here are the guidelines. First, what are the target OS platforms? What kind of inference libraries are available? Are they written in C++ and CUDA? we probably cannot afford a scripting language such as Python due to performance considerations. Next, what are the target GPUs? What is the minimum GPU hardware requirement? When we decide to add AI into game engine, the first rule is AI should not affect the existing game engine functionalities. We will need new threads for AI. Then we should decide the AI response latency target. For dialogue response, people will not be happy if they have to wait for more than 2 seconds for a word. Similar to real-time graphics, one important question we should ask is how often data exchange happens between CPU and AI and graphics. Does it happen within each frame or across many frames? Is there an existing solution to do it on the performance limit? Graphics and AI being scheduled together means they will compete for resources, especially on GPU. It will need careful profiling, and new feature requests arise for tools such as Insight graphics and Insight systems. Okay, now let's see whether we can fit everything into single GPU. For graphics systems such as D3D and Vulkan, the major resources are textures, buffers, pipeline state objects. If you have ray tracing enabled in your game, you will also have ray tracing acceleration structures. AI resources, on the other hand, are much simpler in CUDA API level. They are all linear memories. You can have ASR model, language model, TDS model in your games. And for transformer-based architecture, there are two major parts, width and key-value cache. Width are the static part, and usually stored in model files. Key cache is the dynamic part and can be significantly large during runtime. It grows linearly with context length and can be bigger than width in some configurations. Now let's do a case study about the GPU memory consumption about Llama 2 7B model. This model uses multi-head attention, and the memory required to store KV cache of one token is roughly 2 multiplied by 2 by number of layers, by number of key value heads, and by head dimensions. The first two is for keys and values, two of them. The second two is size in bytes if we use FP16 precision. The number of layers of this model is 32, and the number of key value heads is also 32, and head dimension is 128. So for context length of 4K tokens, for KV cache, it will need 2 gigabytes memory. And with you also use FP16 precision, will need 13 gigabytes video memory. So to do inference with this model, we will need at least 15 gigabytes video memory. Context length is one important factor for both video memory and compute consumptions. Let's see what happened recently about the language model context length. GPT-2 in 2019 had 1K tokens content length and after doubled 3 times. In Llama 3 last year, the content length is 8K tokens. Also in last year for Llama 3.1, there was a dramatic boost of 16 times, and the content length is 128K. So inference with such a long content length is not intended to be done on single GPU. If your dialogue really need such a long content length, you should do it on cloud. With some basic idea about AI model resource consumptions, let's go through a bit of history about NVIDIA GeForce GPU CUDA cores and memory capacities. CUDA cores do programmable shading for graphics. Let's talk about memory capacity first. GTX 1080 Ti started with 11 gigabytes, and the number didn't change for RTX 2080 Ti, the first generation of RTX GPU with hardware accelerated ray tracing ability. Then the memory is increased to 24 gigabytes for RTX 3090 Ti. One reason is that we will need more memory for retracing acceleration structures. The number didn't change for RTX 4090, and now for Blackwell architecture RTX 5090, the memory is increased to 32 GB. CUDA cores generally follow the same trend. Remember that we just talked about for Llama 27B model with FP16 precision, we will need at least 15 GB memory to do inference, and that's just only for language model. So 15 AI models alongside with graphics workload in single GPU seems like a mission impossible task for most of our GPUs. We need to make trade-offs. First, we should choose language model according to GPU memory budget. And generally, we also need to do model weights and cubic head quantization, such as 8-bit or more aggressive 4-bit quantization. Then we should choose a reasonable LLM context length. For GPU memory and compute power considerations, smaller model usually means faster inference, and that's not just because there is less work for memory system. Let's say another important reason. This is a chart about GeForce RTX 5090 compute instruction throughput. I picked several over them. And let's say FP16 is the base one. The throughput is 104.8 TFLOPS. FP16 tensor instruction with FP32 accumulate has 2 times of the base throughput. And FP16 tensor with FP16 accumulate has 4 times of base instruction throughput. FP8 tensor instruction and int8 tensor instruction have 8 times of base instruction throughput. And FP4 tensor instruction, which is new for Blackwell architecture, has 16 times of base instruction throughput. So if quantization is used in your AI model, your inference time will also be boosted accordingly. Let's talk about one important system level optimization. When we feed everything into a single GPU and finish the first prototype, we found that the performance was not good. Top bottleneck after the analysis is that there were too many WDDM content switch happened between 3D graphics and AI. Then driver team and dev tech developed the CUDA in graphics optimization. The basic idea is that CUDA context can be created in CUDA in graphics CIG mode, which means CUDA will share graphics context. DCD12 and Vulkan have been supported. If you are on Windows, you should also turn on hardware accelerated GPU scheduling. In the below left diagram, 3D and AI context kept switching without CIG. One box stands for one WDDM context. On the right, with CIG, 3D and AI will share one context. And the performance has been boosted. Now let's see some raw gameplay performance data. First about content switch activity. In top left image, there are 4 frames. There are many content switch as blue bars. On the right are the screenshots. You can see AI and teammate and the player had many rounds of conversation. In the bottom left image, most of our content switch had been eliminated, and the only left content switch is caused by profiling tool. This is the game end-to-end request latency and the breakdown. On cloud, we use L20 GPU. On device, GPU is RTX 4090. Graphics API is DCD12 on Windows. ASR model uses Perform architecture. NLU uses robot architecture. LLM uses BLADEPOINT 27B architecture. TTS uses with2 architecture. For on-device version, ASR do CPU inference, and NLU and LLM do GPU inference. For TTIs, both versions do cloud inferencing. In the bottom table, end-to-end request latency for cloud version is 750 milliseconds. On device version is faster, the end-to-end request latency is 650 milliseconds. LLM inference is the dominant part for both versions. Let's continue with more details about LLM on-device inferencing. We measure the tokens per second and time to first the tokens. In top table, for tokens per second, there are two phases, prefill phase and decode phase. Prefill phase can be done in parallel, so the number is much bigger. CAG speed up is about 23%. The decode phase, CAG speed up is about 48%. For time to first the token, default time is 225 milliseconds with district detail. With CAG, the time is 160 milliseconds, so the CAG speed up is about 29%. We usually don't do base model inference directly for a game because games usually have special designs and domain knowledge. Serialized language AI needs to leverage techniques such as RAG or fine-tune to adopt domain languages. In the middle diagram for a basic RAG flow, let's say query is about 100 tokens, and after retrieval context could be 1000 tokens. So if RAG is used in your game, and now the LLM needs to process 10 times more input in the prefill stage, and the LLM response latency will increase. In the meantime, it will hold less dialogues, so which means the model will forget things more quickly. So for on-device inferencing, model fine-tune is more friendly in both performance and dialogue quality. As usual, developers don't need to start everything from scratch. NVIDIA provided in-game inference SDK we call NVIDIA. It streamlines AI model development and integration for PC application developers. ISR, LLM, audio-to-face, TTS model are supported. It unifies inference API to orchestrated AI inference seamlessly across PC and cloud. The SDK also supports major inference backend such as DirectML, TensorRT, TensorRT LLM, and GGML. It offers native integration into game pipeline with CUDA and graphics optimizations. Below are the links about NVIDIA repository and one technical blog with detailed code example. Here are the resources for NVIDIA. The supported plugins are Speech ASR, Language GPT, RAG Embed, and different inference hardware are supported, such as CUDA-enabled GPU and CPU, Onyx supported GPU. In the right column, models listed here are available on NVIDIA GPU Cloud website. Okay, that's it. Yeah. Any questions? No, it's nice. 没有问题。
Hi, yeah. So I know this is through NVIDIA ACE, right? And in that final slide, you've got the CUDA supported and then the ONNX supported. So is the CUDA supported, is that only available on NVIDIA hardware? Is that specifically tied to NVIDIA hardware?
Okay, the question is for the NVIDIA SDK, whether CUDA is only supported on NVIDIA GPU. So yeah, I think so.
Right. And when you've so you're about to launch on the 27th the on-device inference for NARAKA, right? Are you specifying, I don't know what platform you distribute it on, but are you specifying like NVIDIA only GPU if you want to do it on device?
Okay, the question is whether NARAKA game identify the NVIDIA GPU on different operating system.
Yeah. 他问那个是不是你们游戏判断
指在 N 卡上的 enable。
Yes, we will detect the PC's the hardware, and we found if the GPU is RTX 3070, and up to 3070, I will use this on-device version, and others will still use the cloud version to support that interact with human players.
So is there a tying of the actual model support with the SDK to compute capability on the cards? So is there a specific data type that was unlocked at a certain compute capability that you're tied to that makes it so that it's 3070 and above? Yeah. Do you know what data type that is? If you don't mind me asking. Is it Int 8 or FP8?
No, I don't know. I think the question is about whether we decide different quantization methods according to the GPU and the GPU architecture and the GPU computer power. Yeah.
Yes.
Right, okay, thank you.
Hi, thank you for the presentation. My question is about the CIG work that you did. How is it, or what is the algorithm you use in order to decide how much of the GPU is dedicated to the 3D graphics and how much is dedicated to the other work? The interleaving is impressive. I'm just curious about whether or not that's hard-coded, or is that something that you discovered empirically, or what?
Okay, the question is for CIG optimization, whether we have ability to decide how much SM, how much computer power are used for graphics, and how much left for AI. Right? So yes, that's a good question, and that depends the workload, whether AI is dominant or graphics is dominant. For NARAKA mobile PC version, the graphics is very lightweight. So maybe for other RTS-enabled games, the graphics workload is very heavy. So our driver team, at the side, is currently developing some options to set how much computer powers are used for graphics and how much are used for AI.
Okay, thank you.
Hi, thank you for NVIDIA and Fuxi Lab's speech. So I have a question for Mr. Liu. What is your motivation about creating those AI teammates? What is your motivation about?
Motivation? Okay.
Yeah.
Just as mentioned that we are discussing with our game developers and the game developers. The first motivation is that the game developer want to make some new gameplay, new game feature in the following for the game to launch. It's the first reason motivation. The second motivation is that just as mentioned that there is some players do not have the human teammate in the games. So we know that there are many AI technologies. We think that this AI technology could to support these players to create the reliable AI teammate to play with them. So I think they're the two motivations.
Yeah, but I think NARAKA is a multiplayer PvP game, and I think that the players will enjoy the confront or the rivaling between the real players. Will you think too many AI teammates will influence this?
Most of the players like to playing with the real human players. Yes, that's true. So this is optional gameplay for the game players. She could choose to use it and could not choose to use it. So it's his choice. So we are the not to so you must to play with the AI teammates. So
all right,
it's his choice.
Yeah, and for Mr. Zhao, I just a quick question. So you said this AI teammates will only work for the NARAKA mobile PC version, and does that mean it will occupy the player's computer the hash rate, like will it influence the player's FPS or not?
Yeah.
The question is whether you will add AI, whether it will affect the graphics FPS. Yeah, that's a good question for us. Yes. I know yes.
Yeah, but in this game, the FPS is really important,
Yes, so at that side, this is the PC mobile version, and the graphics workload is quite lightweight. So the inference, the FPS drops, but it's still in a very high level FPS.
Okay, thanks so much.
Hello. So previously you mentioned that there are future plans to implement like an AI coach for NARAKA that will give you personalized like advice on how to play the game. When I played the game, there was one time was like mashing parry, and then the game pop up like this display that tells me like, oh, calm down, like look for opportunity. In that moment, I feel like it is already personalized. So I want to ask that, are these implementations currently, are they like manually implemented traditionally with like a decision tree or something like that? Or are they already like, there are some like AI stuff going on there?
Yes, that's a very good question. As we know that if we have not personalized guidance, it is very boring, and the players will be feel mad that there is some noise, voice is often will be used, will be found in this game. So we should and must do the personalized AI coach. And the technology we used is some. Now we use some AI technologies. The first one is that we use AI model to recognize the players, the knowledge of these games. So just I mentioned that what the knowledge the new players knows, and which knowledge the players don't know. So we use the players' data to separate two parts, and for one knowledge, the data will be separated into two parts. The first part, we think that the players are not familiar with knowledge, so the behavior is different from those very high-level players. So we train an AI model to recognize the player's behavior data, and using the behavior data to output the whether he knows this knowledge. So this is one of the AI technologies we used in this AI coach gameplay. Yeah. So there are other AI knowledges, because in future we will maybe support the voice interaction. Just I mentioned that to answer the players' questions, and other AI technology maybe also will be used. Yeah.
Oh, very insightful. Thank you.
Okay, thanks for your presentation. I have a question for Mr. Liu. I'm wondering about the reinforcement learning model can conduct many different tasks. I mean that is a reinforcement learning model can input any test command.
Test command?
Yes, test input for reinforcement learning model.
What is that?
The inputs of the reinforcement learning model can include test command.
It's the input of the reinforcement learning is combine the traditional we used in the reinforcement learning, such like the position, the health, the hero type, and the second part is just the command that we will be categorized maybe the 8 or 9 types, and maybe just I said that to attack the first enemy, and the data command will be set as the category type into the reinforcement learning. And the reinforcement learning, the training process of the reinforcement learning will be trained by this combining the command, the reward, and the battle reward, and to make the decision that how to achieve the final result. Yeah.
So it's maybe a multitask reinforcement learning.
Yes, multicast.
Okay, thanks for your answer.
Hi. I have a question. So your colleagues introduced cooperative vectors, I don't know, recently or last 2 days. So I'm wondering if you see if this technology is suitable to replace CUDA here, or you think the CUDA in your application here, or you think that's not applicable because you want the CUDA part and the graphics part to run asynchronously without interfere the frame generation. Do you think the cooperative vectors are using using the tensor core in the graphics pipeline is suitable for this task?
Okay, the question is, I think your question is whether if graphics can use tensor core, we will replace many CUDA kernels by graphics kernels, right? Such as a computer kernel.
Yeah, I think your colleague just introduced the new features in the DirectX 12 API that you can use it now, or in the future you can use tensor core inside the graphics pipeline. Have you ever think of whether like putting part of the AI task inside the graphics pipeline is a suitable solution, or is or it's not because you don't want it to be synchronous?
I think that's a very interesting idea, and it can be done in very low level in the drivers. It can be done, but I think it hardly depends on the habits of the application developers.
Okay.
We can do it.
Okay. All right, cool.
Hello, sorry, this will be my last one. So you train you have a reinforcement training loop. What part of the pipeline is that being applied to? Is that being applied to the ASR, or is it the LLM and the ASR, or the LLM on its own? I know that there's the pathfinding, but is that a separate model to the LLM, or is that within the LLM, ASR, LLM, TTS pipeline? Yeah.
It's separate. That it's not an end-to-end solution. Yes, there are many other models in the process.
Right.
Yeah.
And what part of that process, those separate models, does the outputs actionable kind of elements? How do you extract? Is it that you do inference on the textual output to create kind of because you've got the characters actually going and moving in the world, right? Or picking something up. How do you actionably translate those AI outputs into those in-game actions?
That's just let's show the agent assistant. Can we see in this picture that there's a decision-making system module? Yes, the decision-making system is a high-level decision, and it will decide we should to do the combat or the searching for the equipment, and then the decision-making system will give the decision and to call the appropriate module to do the things. So it is a high-level decision module. Yeah.
Right, and then the reinforcement learning model is the only one that can do real-world actions.
Yeah.
Thank you so much. Brilliant talk, by the way. Thank you.
I have 2 points about your question. Because in NARAKA, you can move like a Spider-Man. So there is a navigation mesh. They use reinforcement learning, and there is a dedicated model for it. For on-device, the model is run on CPU because the model is very small, and we usually cannot beat the CPU when the model is very small.
Because it has, just I mentioned, the hook system. So you could use the gambling hook to reach every visible place. So it is very hard for navigation. They just never mesh, just the traditional method to have the high level capability to navigate in the games. Just either in the wall in these rooms, in the NARAKA mobile, something like these rooms, it can get everywhere in the games. You can use the Gabriel hook system.
And is the decision-making model's output, is that like a discrete, like, are you actually entering text as a prompt to the reinforcement learning model that then directs how you represent that goal, that decision brackets goal? Like, what's the representation of that?
They will go send into the reinforcement learning, but the output of the reinforcement learning, just like the navigation model, it is the role action, just like the human players doing that. Turn. Yeah.
But if we are run out of time, and we can discuss outside the room. Thanks, guys.